We share
theoretical and empirical reviews.
It is all about learning research facts and sharing with others.
Please subscribe to our channel if you like our videos.
Title of the published report:
Numerical modeling of the hydrodynamic stability in vertical annulus with heat source of different lengths.
Details of the published report. Author of the published report.
Introduction. Internal heating. Size of the heater. Convection is the transfer of heat due to the bulk movement of molecules within fluids, gases, and liquids, including molten rock. Heating of the surface is a well-known method of establishing convection. In such a case, density differences are sufficiently small to be neglected, because it is going to be a multiplier of the acceleration due to gravity. During the process of heat generation, some scholars explained the role of thermal conductivity, which is the ability of fluid and any other materials to conduct heat. But, in the case of cooling the surface, heat sink is inevitable. It was remarked in the report that heat generation affects not only the temperature distribution, but also the particle deposition and molecules that form the fluid substance. Internal heat source or sink can be uniformly temperature dependent as modeled by some scholars. Internal heat source or sink can be space dependent as modeled. Internal heat source or sink can be temperature and space dependent as modeled. Internal heat source or sink can be temperature dependent and product of the difference in temperature and velocity as modeled. In the year 2019, some scholars examined the significance of heat source of different lengths on the heat transfer inside a horizontal channel with an open trapezoidal enclosure and noticed that the maximum value of the average Nusselt number corresponds to the highest length of the heat source. The local Nusselt number increases as the local heat source length increases. The increase in the heat source length leads to a slight variation in the pattern of the velocity contours. Thermal convection of water alumina nanoliquid in a chamber, having a fin thermal sink and a heat-producing local unit was simulated by Sheramet and Rashidi, 2021. The results show that average heater temperature decreases with volume fraction for a low non-dimensional height of the radiator fins and high Rayleigh number, or high non-dimensional height of the radiator fins and low Rayleigh number. In a study of the dynamics of water conveying titania nanoparticles, B. ethylene glycol conveying titania nanoparticles, and C. engine oil conveying titania nanoparticles by Mebarek-Oudina, 2019, the significance of discrete heat source was mentioned, though it was fixed in the simulation. Dynamics of four nanofluids through a porous medium, situated in the cylindrical annulus with radii Ri and are not subject to Lorentz force was examined by Mebarek-Oudina and others, 2020, using the Darcy-Brinkmann model for the porosity. The four nanofluids are water-based nanofluid made up of copper nanoparticles, B. alumina nanoparticles, C. silver, and D. titanium dioxide, also called titania. The analysis of the study by Mebarek-Oudina and others, 2020, led to the conclusion that the average Nusselt number declines due to an increase in the size of the heater. The average Nusselt number was found to be maxima at all the increasing size of the heater. However, the same property is minima and linear as the size of the heater increases. In a study on the dynamics of unsteady ethylene glycol conveying graphene nanoparticles through a porous medium, Rohit Sharma and others, 2021, noticed that in the case of a slip, an increase in the heating of the fluid causes Nusselt number to increase at the rate of 0.05535515. But, in the case of no slip at the wall, an increase in the heating leads to increasing Nusselt number at the rate of 0.05555285. Based on the outcome of this study, it is worth concluding that slip at the wall causes the Nusselt number to be higher at each level of heating of the fluid. It implies that heat transfer is very fast in the case of no slip and slows in the case of slip at the wall. To further understand the significance of exponential heating of gases, a study on the significance of Cortic autocatalytic chemical reaction by some scholars in the year 2020 was considered. The results of the study show that when the exponential heating of gases is small, the concentration of dusty fluid at the wall is small. But when the heating of gases is large, the concentration was also found to be higher. When the exponential heating of gases is small, the concentration of the catalyst at the wall is large. But when the heating of gases is large, the concentration was found to be lower. The observations above were true at all the levels of the fluid-particle interaction for velocity, surface tension, buoyancy, the inertia of induced liquid motion, Marangoni or thermocapillary effects, and bulk fluid motion not only act to influence departure diameter, but the magnitudes of these forces are functions of bulk subcooling, sub, gravity, wall superheat, set, the thermophysical properties of the fluid, heater geometry, surface characteristics, and pressure. This study indicates that the geometry of the heater or the object causing the heating can affect surface tension, buoyancy, the inertia of induced liquid motion, Marangoni or thermocapillary effects, and bulk fluid motion. In a study by Henry and Kim, 2004, to determine the effects of heater size, subcooling, and gravity level on pool boiling heat transfer, it was discovered that in low gravity, a reduction in heater size appears to decrease satellite bubble formation. Besides, the heater size appears to strongly affect thermocapillary induced heat transfer that occurs post-critical heat flux, CHF. In high gravity, heater size appears to strongly affect bubble departure frequency by placing limitations on the size of a growing bubble. In summary, it appears that the size of the primary bubble relative to the heater size determines the heat transfer. An attempt was made by Sheramet and Pop, 2018, to study the natural convection heat transfer within nanofluid porous cavities with local heaters. It was discovered that the heat transfer enhancement and convective flow attenuation when the distance between the heater and the cold vertical wall reduces. In a study carried out by GUO and others, 2019, to investigate the performance of downhole electric heaters with continuous helical baffles, it was disclosed that generating high temperature fluids with downhole electric heaters can reduce heat losses along heat insulation pipelines.
Next, we shall now present the theoretical review.
The study by Mebarek-Oudina, 2017, was designed to study the natural convection heat transfer stability of a two-dimensional unsteady Newtonian fluid flow through a vertical cylindrical annulus formed by two vertical concentric cylinders. The radius of the inner cylinder is Ri and that of the outer radius is R0, thus the annular gap is R0 minus Ri. It was assumed that there exists a finite-sized heater of length L placed at the wall of the inner vertical cylinder, thus the heat flux generated by the heater covers the annular gap.
Based on the introduction, critical appraisal of related published facts, next is to now present the empirical review of the study by Mebarek-Oudina.
The results obtained by Mebarek-Oudina, 2017. Figure 12, show that for epsilon equals 0.2 there exists a large value for the Nusselt number and epsilon equals 0.8 leads to a smaller value of Nusselt number for Z strictly between 0.1 to 0.8. In other words, heat transfer is very slow when the length of the heater is small, epsilon equals 0.2. But, when the heater is very long, epsilon equals 0.8, the rate of heat transfer was found to be very fast. These results are true, because the heat transfer rate is inversely proportional to the well-known Nusselt number. These results are true, because the heat transfer rate is inversely proportional to the well-known Nusselt number. The observation above was also confirmed when the Rayleigh number, that is product of the Grashof number and the Prandtl number, is small and large in magnitude, see figure 8a and figure 8b. The only exception is that the magnitude of the Nusselt number n_u is small when Rayleigh number equals 10 raised to power of 4, and it is large when Rayleigh number equals 10 raised to power of 8. It is realistic to conclude that Rayleigh number equals 10 raised to power of 8 characterizes the fluid's flow regime as a turbulent flow, and worthy to conclude that the transfer of heat across the domain for the case Rayleigh number equals 10 raised to power of 8 is very slow, just because of the chaotic changes in pressure and flow velocity. This is very clear in figure 9, where it is shown that the temperature distribution for the case Rayleigh number equals 10 raised to power of 8 is less than 0.054 Z, strictly between 0.05 and 1. In summary, it is worth concluding that as an increase in the length of a heater is capable to enhance heat transfer rate, convection can be used to minimize temperature distribution and the rate of heat transfer across the dynamics due to turbulence nature.
Acknowledgements.
Special thanks to all the editors and reviewers of Engineering Science and Technology, an international journal, Elsevier. We Share Tour appreciates the contribution of the authors to the body of knowledge. We share
Theoretical and empirical reviews.
It is all about learning research facts and sharing with others.
Please subscribe to our channel if you like our videos.